Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching PU2 Brahmastra series, where we are trying to help you to achieve maximum score in your PU2 final exam. Today we are going to discuss a very important chapter from your physics, that is electromagnetic induction. In terms of coverage etc, we will discuss that, but before that you have to join our WhatsApp channel to get all the latest notification and all the chapters that we have already covered in our series. You can check the description below for the link of the playlist, also for the link of the our WhatsApp channel. So let's see the weekly schedule for this week's chapters. So we have already know that Monday ma'am already completed biomolecules. Today I am going to cover electromagnetic induction. Tomorrow biology, human reproduction. Then Thursday again chemistry, D and F block. Friday I'll be back with alternating current. Then Saturday as usual there will be two classes, one for maths, one for biology. Integration and evolution will be the chapters, and Sunday integration part 2. So your integration will be completed by Sunday. Okay, I hope that clarifies any doubts you might have that what will be the weekly schedule, that I have already given it to you. Now next, what are the chapter wise weightage for this chapter? Blueprint 1 says that there will be two MCQs. Okay, one will be remembering based MCQ, one will be HOTS question MCQ. Okay, blueprint 2 says there will be only one MCQ which will be HOTS. HOTS means higher order thinking skill, which is slightly difficult, where you have to analyze the question. Okay, there will be no direct question from this chapter. But blueprint 3 says there will be only remembering based MCQ. So blueprint 3 gives it relatively easy. So any type of questions can come from this chapter, either remembering based or HOTS question. So as you can see, two of them are saying HOTS question, two of them are saying remembering based question as well. Now what is the fill in the blanks? Fill in the blanks, blueprint 1 there is no fill in the blanks. In blueprint 2 there is only one fill in the blanks, and in blueprint 3 also one fill in the blanks from this chapter. Okay, now short answer type 2 marks question, there will be one. Blueprint 1 says one understanding based question, blueprint 2 says one understanding based numerical problem from this chapter. So there may be one numerical problem can be expected as a 2 marks small answer type question. Okay, again blueprint 3 says only one understanding based question. Okay, in 3 marks category again one understanding based question according to blueprint 1. According to blueprint 2 there will be numerical based question, and according to blueprint 3 there will be only understanding based question. So these are the 3 blueprints. So we have understood that there is no 5 mark long answer type question from this chapter. There is no 5 mark numerical problem from this chapter. Okay, so you can skip the numerical problem for this chapter as there is no important numerical questions. But 2 marks and 3 marks you have to practice some numericals. Small numericals will come from this chapter. One of the numerical definitely will come from this chapter as a form of 2 marks question. Okay, now what all we are going to discuss in this lecture today? We will be discussing as usual 15 MCQ questions. We will be also discussing fill in the blanks 5, because fill in the blanks is important for this chapter. Then we will discuss short answer type 2 marks question 5 and short answer type 3 marks question 5. Okay, so there are total 30 questions we will discuss today in our lecture. I hope that will be very helpful for you, because this is an easy chapter, scoring chapter. You can easily score 7 marks if you study this chapter properly. Okay, now let's start with the MCQs. The energy stored in an inductor of inductance L in establishing the current in it is. So the energy stored in an inductor is half Li square. The formula for that is half Li square. So the correct answer is option D. Right, next question. The following are the statements related to the self-inductance. So this is a HOTS question. Previous one was a remembering based question. So you have to understand the difference between HOTS question and remembering based question. HOTS question are not difficult inherently. There you have to identify and answer. The self-inductance of a coil depends on its geometry and on the permeability of the medium inside it. Yes, statement 1 is correct. We know that self-inductance depends on the geometry. The self-inductance is a measure of electrical inertia and opposes the change in current in the coil. Yes, that is also true. Okay, both the statements are true. So this is called electrical inertia. The self-inductance is called electrical inertia. So both statements are wrong. Only statement 1 is correct. Both statements are correct. So both statements are correct. So option C is the correct answer for this question. Okay. Next question. The direction of current induced in the loop ABC shown in the figure is. Okay. So here, as you can see, the current is flowing in this direction. Okay, so first we have to find the magnetic field in this direction. What is the magnetic field induced? Whether it is into the paper, whether it is out of the paper. So first, when there is a straight wire, I said this in our previous classes also, if you are following my cassette class, if the current is flowing in this direction, okay, first you have to orient your thumb. For straight conductor, you have to use your thumb. Okay, you point your thumb towards the current. Once you point your thumbs towards the current, stretch your hand, then bend your fingers like this. Okay, if you bend your fingers like this, then this finger will point the direction of magnetic field. So in the case of straight wire carrying current upwards, the magnetic field will be into the paper, and into the paper we denote it like cross, because you can throw something in the cross, right? So like a dart. So into the paper, the magnetic field is for current in this direction, magnetic field will be into the paper. Now let us consider this circle. Okay, so the current will be in the circle such that A, B, C. The current in this circle will be such that this opposes the original magnetic field. The induced magnetic field in the loop will be such a way that it opposes the induced magnetic field. So what will happen? The magnetic field will be in this direction. The induced magnetic field in the circle, in the loop, will be outward direction. Right, so let me represent the induced. Just a second, give me a second, so that any confusion will be gone. So this is the magnetic field due to this loop. Now let me construct the loop in a different color so that you don't get confused. Now this is A, B, and this is C. Okay, now the induced current in this loop will be such a way that this acts outward direction. That is, the induced field will be like this. This is the induced field. Now if we want to find the direction of current such that the induced field is outward direction, then how to do that? For a loop, first of all, if the magnetic field, direction of magnetic field is known, then we will point our finger in the direction of magnetic field. In this case, this is different than a straight wire, right? In case of straight wire, we point the finger in the direction of current. In case of loop, we point the thumb in the direction of magnetic field. Okay, so this is the magnetic field. So current will be flowing in this direction, that is CBA. Okay, no, they have asked is along ABC if it is increasing, along ACB if it is decreasing, along ABC if it is decreasing, along ACB if it is constant. So basically constant does not have anything to do. Only thing, if it is increasing, that means magnetic field is increasing inside, right? So if the magnetic field is increasing, then it will be ACB, so that it comes outward. Okay, so it will be along ACB if it is increasing, but as we can see, for ABC it is increasing, so ACB is definitely not possible, it's decreasing. So it will be along ABC if it is decreasing. So decreasing means it will be inward direction. Why? Because magnetic field is increasing, so this loop will try to increase that. Whatever the change is being caused, by default, if it is only increasing, it will be along ACB. Okay, but it is not by default. They have changed the question, they have twisted the question, so that they are saying if it is decreasing, then only it will be inward direction. So in this case, the loop, the magnetic field will also be in the inward direction. Okay, so induced magnetic field will also be in inward direction. Okay, this is slightly hot question, so you maybe find it difficult to answer. So it will be in this case A, B, C, because it is decreasing, right? So in decreasing means thus this induced EMF will try to increase the induced EMF. Okay, very important but very delicate concept, very small interesting concept, so you have to understand that. Okay, so first of all, ACB will be happening only if it is increasing, right? But ACB is they have given the option for decreasing, so we understood that ACB is possible for increasing, so definitely decreasing is not a viable option. And in case it is increasing, then definitely it was ACB, not ABC, so definitely this is also ruled out. So if you understand one concept, you can directly rule these two options out. Okay, secondly, it is constant. In case of constant current, there is no change in the magnetic field, so induced EMF will be 0, induced current will be 0. So by method of elimination also you can answer option C. You just find what is the direction of current if it is increasing first. Okay, now check if that option is given in the as a option or not. If it is not given, then definitely you can rule out two of the given options. Third option will generally be constant, so constant one also you can neglect. So whatever the fourth option left, that is your answer. Okay, this is how you can do the method of elimination as well. Now the polarity of inductance EMF in a coil is given by, so we know that the EMF, the value of EMF is given by Faraday's law, but the polarity is given by Lenz's law. Okay, so Lenz's law is the answer because that adds the negative sign. If you remember, the induced EMF is given by minus d phi by dt. Now Faraday's law says this induced EMF is directly proportional to the flux linked with the coil. It does not talks about any sign. Okay, Lenz's law says that the original induced EMF will be such that it opposes the cause that is creating it, right? So that negative sign is comes because of this Lenz's law. So basically this negative sign is the Lenz's law. So answer is Lenz's law. Now this question can come in a different variation as well. Which of the following is a consequence of conservation of energy? The answer is again Lenz's law. Okay, this comes because of the conservation of energy. We will discuss in one of the short questions where this question comes, explain why Lenz's law is related to conservation of energy. So we will see why it is related to conservation of energy, right? So you have to remember that this question can come in different forms also. Sometimes they will ask you which of Lenz's law talks about dot. There you have to identify conservation of energy. So Lenz's law talks about conservation of energy. Also it gives the polarity of the induced EMF. Next question, current in a coil changes from 1.6 ampere to 0.2 ampere in 2 seconds, inducing an EMF of 2.8 volt. The value of self-inductance of the coil is. So we know that induced EMF is L di by dt. There is a negative sign, but we are not interested in sign in this case. Okay, but we will find this, what is the value given. So we know that induced EMF is given by 2.8 volt. Okay, L we don't know. So what is di? Di is change in the current. Current changes from 1.6 to 0.2. So the change in current is 1.6 minus 0.2. And what is the time? Delta t or dt is the time. Time is 2 seconds. So it will be 2 seconds. So it will be L times 1.4 divided by 2. Okay, or it will be 0.7 L, right? So L will be 2.8 divided by 0.7, that is 4. Okay, so the answer is 4 Henry. Self-inductance of the coil is 4 Henry. Simple question. If you remember the formula, just put the values. Only thing you have to remember, di represents the change in current and dt represents the time interval. Okay. Next question. The SI unit of mutual inductance of a pair of coil is. So unit of mutual inductance, unit of self-inductance is always Henry. Okay, Henry, millihenry. Okay, sometimes they might give you Henry or sometimes they may give you millihenry. Both are correct. But if you can eliminate the options as well. Farad is the unit of capacitance, ohm is the unit of resistance, ohm meter is the unit of resistivity. Okay, ohm meter is the unit of resistivity. So you can, from there you can also ignore this. Also you have to remember this should be small h. Henry should be small h. These are all should be small. Okay, small letters, because capital Henry represents the name of the person, right? Henry unit is small h. So now let's look into the question number 7. Which of the following quantity is measured in Weber per ampere? So from this, Weber is the unit of magnetic flask. You have to remember that Weber is the unit of magnetic flask, and Weber per ampere is the unit of self-inductance. Okay. Now from this question it might seem you easy that all the options, because you are talking about only magnetic field, okay, but when you are writing the exam, electric flask is also important, okay, electric field is also important. So but from this point of view, when you are seeing this as a chapter question, you know that this is based on electromagnetic induction, so only magnetic flask or self inductance is possible. Now magnetic flask's unit is Weber. Okay, so electric flask is we know that it is electric field times area. Okay, so you can calculate the unit of electric flask as well. Weber definitely means it is related to magnetic field, and it is not magnetic flask, so this is definitely it's a self inductance. Okay, so Weber per ampere is the unit of self inductance. An AC generator, what is the AC generator? A device used to convert electrical energy to mechanical energy. A device used to convert mechanical energy to electrical energy. Both A and B, none of the above. So we know that AC generator is basically a device which generates electricity, right? Generator means which generate electricity, right? So as we know, so mechanical energy to electrical energy, so option is option B. It converts mechanical energy into electrical energy, right? So that's why it is called AC generator. Okay, AC motor, if the question was AC motor, motor works on the electricity. You give electricity, it gives you mechanical energy. For example, the motor that pumps the water from ground level to your rooftop, right? So that is called motor. Motor is what works on electricity, converts it into work, right? And generator is something which works, which mechanical energy is given as input, and it converts it into electrical energy. The SI unit of mutual inductance, again Henry, as we know, mutual inductance, self inductance for all unit is Henry. The expression for motional EMF. So motional EMF means when there is a loop, okay, you have done this, a coil, a line element is moving with a velocity v in a loop, okay, whatever the EMF is induced on the end of this line, so that is given by BVL, no sin theta, no cos theta. Okay, it is only simply BVL, no sin theta, no cos theta. Next, the magnetic flux through a surface area A placed in a uniform magnetic field B is defined as, the magnetic flux is defined as B dot A. Magnetic flux is a scalar quantity. Okay, you have to remember that magnetic flux is a scalar quantity, so it is not a vector quantity. It will be BA cos theta or simply BA B dot A. Okay, sometimes they might give you the option BA cos theta. Okay, BA sin theta, B by A cos theta, B by A sin theta, like that they might give, but you have to remember that magnetic flux is a scalar quantity, so if they ask you in terms of vector, you have to identify that because it's a scalar quantity, it will be definitely a dot product, cross product option. All the options related to cross product should be wrong. Okay, the induced EMF in a coil, the magnetic flask linking must remain constant, must increase, must decrease both B and C. So to induce a current in a coil, okay, the magnetic flask linked with the coil should change. It can increase, it can decrease. So basically option is option D here, both B and C is possible. It can increase, it can decrease, both cases there will be some induced EMF. This is a very tricky question. So you might see that must increase, must decrease, so maybe it will only remain constant. If it is remaining constant, there will be no induced EMF in the circuit. You have to remember that in case of constant linkage of flask, if the flask does not change, d phi is 0. If d phi is 0, in that case there will be no induced EMF. when a magnet is moved with its n pole towards a closed coil, the nearer end of the coil acts as. Now you can draw the diagram, you can do the all the mathematics, but you have to remember the basic fundamental principle of Lenz's law, that when a magnet is moved with n pole towards the closed loop, the closed loop will try to repel that magnet. So the fundamental principle of Lenz's law, that any change occurring into a system, it will try to prevent that. So how can you prevent a north pole coming towards you? By developing a north pole yourself, right? So by developing a north pole yourself, what it will do, the coil will try to repel the north pole, incoming north pole. If it is going away from the loop, then it will develop a south pole, and then it will try to stop that motion, away motion. It will try to then attract it. Okay, so this is the basic fundamental principle of electromagnetic induction. So it will be north pole is the answer. The magnetic flux linked with the coil varies as phi equals to 2t square plus 2t. What is the magnitude of induced EMF at t is equal to 0.5 second? So we know that induced EMF is given by d phi by dt. Okay, so simple integration that you have to do. D phi by dt, so it will be 2 times 2t. Okay, t square, right? T square means differentiation of t square is 2t, right? So 2, this 2 is the constant one, first one, right? Next 2t is coming from the differentiating t square plus 2t. Now differentiate this. Differentiation of t with respect to t is dx by dx. In this case dt by dt, that is 1, right? So here it will be 1. So it will be 4t plus 2. Okay, simple. Now what is the magnitude of induced EMF at t equals to 0.5? So what you have to do, you have to put the value t equals to 0.5, that is 4 times 0.5 plus 2. So 4 times 0.5 is 2, 2 plus 2 is 4. Okay, somehow the options are not correct. So options will be, one of the option will be 4 volt. Okay, say 1 volt, 0 volt, 5 volt. Okay, so the option will be 4 volt. So here will be option B will be correct answer. Now the last MCQ question, the SI unit of magnetic flask is, we already answered this question. SI unit of magnetic flask is Weber. Okay, so SI unit of magnetic flask is Weber, not Tesla per meter square, not Weber per meter square, not Weber per meter square. Okay, Tesla meter square is still a viable option because it is magnetic field times area, right? So if it is Tesla meter square, then definitely it is a possibility, it is a same thing as Weber. Weber is another name for Tesla meter square, right? So this represents the magnetic flask. Okay, so now let's move on to the next part of the question. The device which works on the principle of electromagnetic induction is, so the device that works on the principle of electromagnetic induction is, from the given option you can see only AC generator makes sense. This is only one device is mentioned, all the other options are not a device. Okay, magnetic potential energy, conservation of energy, inertia, AC generator allows opposites. So as I said, whenever you are answering, fill in the blanks, try to make sense of the answer. If it is making no sense, then definitely your answer is wrong. Okay, so device means it will be a device. Now in the given option, maybe in the exam there will be another option which says say transformer. Okay, transformer is also a device, so you have to be careful. So you have to, first of all, you have to eliminate. If you don't know the answer, eliminate by making whether the option, given option that I am putting here is, if it is making any sense or not. So only from this given option only AC generator makes sense, so the answer will be AC generator. Next question, the Lenz's law is based on conservation of energy. Okay, so this is conservation of energy. We know the answer, so we answered it directly. Next question, self-inductance plays the role of, let's see, magnetic potential energy, no. Inertia, yes. Self-inductance plays the role of inertia. Inertia means it prevents the build-up of EMF. That's why it is called inertia. It prohibits, is try to stop it. That's why it is called inertia. Okay, energy is stored in an inductor in the form of, so if can you see any other energy form? How many energy forms are there? Magnetic potential energy, only one energy form is there. Okay, allows opposites are not the form of energy, so only option answer will be magnetic potential energy. Now for in this case, this long gap gives you a hint, so basically the option will be long because I am inserting it using animation, so that's why it is like that. Okay, induced EMF always dash any change in the magnetic flux. Now in this case there can be two options. Okay, either it will be allows or it will be opposite. So in this case they have given you the option, so that both options is possible, logically possible, but which one is correct? So induced EMF always opposes, that is the Lenz's law, right? Lenz's law states that induced EMF always opposes any change in the magnetic flux, so answer is opposes. Okay. Now let's look into the question. Now we are into the 2 marks category. Give the principle of AC generator, why it is a current induced in an AC generator called an alternating current. Mention the expression for inductance EMF on it, induced EMF in it. Okay, let's see the answer. So an AC generator converts mechanical energy into electrical energy by changing the flask linked with the rotating coil. The direction of the current produced in an AC generator changes periodically, and therefore the current is called alternating current. Now the expression for induced EMF for a AC generator is given by epsilon equals to NAB omega sine omega t. You can check in the book how this formula came, but formula how this it arrived is not important. Important part is what are all these quantities. N is number of turns in the coil. Okay, A is area of one single coil, right? B is magnetic field, and omega is obviously angular speed. Okay, now if you see, this question is not a 2-mark question. Generally principle and why current is induced is called AC is 2-mark question, but sometimes they might not ask the why it is called AC. Instead they might give you mention the expression for induced EMF in it. Okay, so basically then in that case you have to answer this. This is the, or this entire question might come as a 3-mark question. Okay, so instead of giving it as a 3-mark question, I am giving it as a 2-mark question, because in your blueprint only first 2 part is given as a 3-mark question. But I have seen one of the exam paper where they asked the value or the expression for induced EMF as well. So that's why I have included that in this question. So this is a basic, very possible chance of coming as a 2-mark question. Only 2 part of this question will come as a 2-mark question. Okay. Now let's move on to the next question. State Faraday's law and Lenz's law of the electromagnetic induction. So the time rate of change of magnetic flux through a circuit induces EMF in it. So induced EMF is basically proportional to the change of flux linked with the coil. Okay, linked with the closed circuit. That is the basic Faraday's principle. Second law, that is Lenz's law, states that the polarity of induced EMF is such that it tends to produce a current which opposes the change in the magnetic flux produced it. So from the Lenz's law it is minus d phi by dt. So the constant of proportionality is -1, that is Lenz's law. So combined you have to write these 2 expressions as well. So by writing these 2 you will get the full marks. Now next, question number 23. Mention any 2 factors on which the self-inductance depends. Okay, the equation of self-inductance, very important to remember, mu naught n square A L. Okay, so n square is number of turns per unit length, A is the area of the coil, whatever coil that you are considering, L is the total length of the coil. So basically length means not the length of the wire. So if this is the coil, suppose, okay, this is L, the total length is L. Okay, this is area, and how many turns are there in unit length, that is N. Okay, this will help you to remember. Okay, so mu naught is constant, obviously. Free space permittivity, permeability. N square is the total number of turns per unit length. So self inductor is directly proportional to the square of the number of turns per unit length. Okay, you can mention L proportional to N square. Self inductance is directly proportional to the cross sectional area A of the solenoid. So basically you can say that L is directly proportional to, in this case you can mention L is directly proportional to area. Okay, and self inductance is directly proportional to the length of the coil. Okay, length of the solenoid. Basically we are talking about a solenoid. Okay, solenoid means this is the solenoid. Okay, now this is the self inductance, how you can calculate the self inductance. Okay, now next question. A boy pedals a stationary bicycle. So this is a numerical based question. Okay, I said there may be numerical based questions as a 2-mark question from this chapter. So let's see one numerical based question. A boy pedals a stationary bicycle. Okay, the pedals of the bicycle are attached to the coil of a 100 turns. Okay, each turn of the area. So area of each turn is 0.2 meter square. The coil rotates at 6 rotations per second. So total coil rotates 6 rotation per second. And it is placed in a uniform magnetic field of 0.01 Tesla, perpendicular to the axis of rotation of the coil. Okay, so the coil is rotated like this. So area of the coil is given, total number of turn is 100. Okay, they ask you to calculate the maximum value of EMF generated in the coil. So it's based on AC generator. We have seen the expression for AC generator is NAB NAB omega. Right, so if you can calculate N, A, B and omega, then you can find this maximum value. Sin omega t, there is a sin omega t, maximum, for maximum value you know that sin omega t equals to 1. So this is expression is not only important for your question to answer, this is also important to solve the simple formula based numerical question. If you know this formula, you can answer this question. This is a simple calculative problem. Okay, only thing that you have to calculate is omega. Okay, how to calculate omega? Omega is basically 6 turns per second. So what is the angle rotated in 1 turn? So you should know that when it is rotated by 1 turn, it is pi plus pi, that is 2 pi. Okay, so 6 rotation per second. So total number of angle that it subtend will be 6 times 2 pi radians per second. So it will be 12 pi. That's it. Okay, now put the values. N is given as 100. Area of the coil is given 0.2. Magnetic field B is given as 0.01. And omega is given 12 pi. We have calculated omega as 12 pi. That's it. Nothing else. Okay, so you can see this will be 100 and this will cancel. Okay, why? Because 0.01 means 1 by 100. Okay, so 100 and 1 by 100 will cancel. 0.2 times 12 pi, so 2.4 pi volt. This is the induced EMF. You can put the value of pi 3.14414 and calculate the value, or you can leave it here. Both are correct. Okay, so if you put the value, you will get 7.54 volts. Okay, so if you put the value of pi, you will get 7.54 volt, but this is also acceptable answer. Next question. An aircraft with wingspan of 40 meters flies with a speed of 300 meter per second in the eastward direction at a constant altitude in the northern hemisphere, where the vertical component of the Earth's magnetic field is 1.75 10 to the power of minus 5 Tesla. Calculate the EMF developed between the tips of the wings. Now the vertical component individually is not part of the syllabus anymore, but they might say that the vertical component of the magnetic field at that location. So this is a valid question. Okay, you might think, sir, vertical component is no longer part of there, but this, since they have ignored, I have ignored any other components, and directly the magnetic field is given, they might say the perpendicular component of the magnetic field or the magnetic field acting perpendicular to the motion is given by this. So that is basically the magnetic field that is given to you. Okay, and this is basically a problem based on the motional EMF. We have learned the formula BVL. So the B is given as 1.75 times 10 to the power of minus 5. Okay, velocity is given as 300 meter per second. Okay, L is the wingspan. Wingspan means when the plane is flying like this. Okay, the plane is flying like this. Okay, so this is the plane. Okay, this is the cockpit. Okay, this is the wingspan. Okay, and there will be some induced EMF in the edge of the wing. Okay, this is the wing, so this is 40 meter. It is flying east, and the perpendicular component of the Earth's magnetic field, that is 1.75 times 10 to the power of minus 5. Now what is the EMF generated between the ends of the wingspan? Okay, that is the main thing. So you have to multiply it with 40. BVL, B we know, V we know, L we know. Just simply put the value, get the answer, kind of a question. So it will be so let's calculate it. 1, 2, 3. So 10 to the power of minus 2. Then it will be 3, 12. 4 times 1.75. 4 times 1.75. 1.75 means 4, 2, 3, 7. Okay, 7 times 3. So it will be 21 times 10 to the power of minus 2, or 0.21. Okay, 0.21 volt will be the answer. Okay, you can use your calculator to calculate it. I used my mind because I don't use calculators, so that's why my mind is trained. So you will get the 0.21 volt as the answer. Okay, now derive the expression for motional EMF induced in a straight conductor moving perpendicular to uniform magnetic field. So here we have a coil. Okay, so you have to draw this diagram. Okay, I have taken this diagram from your book. You have to draw this diagram for this derivation. This is a 3-mark derivation, right? So first of all, the cross represents magnetic field into the paper. Okay, this is the motion. Okay, and this is the length. Okay, how much flask is initially linked with this coil. The flask linked with this coil is the area times the magnetic field, right? So the flask linked is area into magnetic field. Now what is the change in the flask? Okay, suppose this is moving with a velocity v. After some time it reaches to a point here. Okay, so suppose this is the distance dx. Okay, and the time taken for this is dt. Okay, in dx, in dt time, it covered a distance dx, right? So what is the change in the flask? Change in the flask is the flask linked with only this portion, right? So what is the induced EMF? Induced EMF is given by change in the rate of change of flask through it. Okay, what is the flask changed in it? Flask changed is dx times L. Okay, dx time L. Why dx time L? We have to calculate the area, right? This small area. What is this small area? Dx is the length, dx is the width, and L is the length. Length into width is the change in area. So change in area can be written as dA equals to L dx, length into breadth, right? Here breadth is dx. So change in area is this. Now change in flask d phi is basically magnetic field times change in area. Okay, so this is the change in flask. So what is the induced EMF? Induced EMF is d phi by dt, that is equals to B dA by dt. Okay, now B is obviously constant, B is not changing in this case. Let me write it like this. B dA by dt. Now B is constant, so definitely it will come out of the differentiation, right? Now what is dA? dA is L dx. So put that value here, B L dx by dt. Again L is constant, so we do not need to include it in the differentiation, so L will also come out. Okay, so what is dx by dt? Dx by dt is rate of change of distance. So how fast it is moving in this direction. So what is the measure of dx by dt? So dx by dt represents the velocity. You remember in your first PU you have learned that velocity is dx by dt, ds by dt, right? Here also dx by dt is the velocity, how fast it is moving. So it is bvl. In bracket you can write dx by dt is the velocity, right? So rate of change of displacement, that is V. So induced EMF in this case is given by BVL. This is the expression for motional EMF, right? So this is the expression for motional EMF. You have to write all the steps. You have to write change in area, you have to write change in flask, then you have to do the calculations to get the full marks. So write these two parts, you get 1 mark. Okay, if you write do the derivation properly, then you will get if you write this part you get 1 mark. My mistake. If you write change in area, 1 mark, including change in flask. If you miss any one of them, the teacher can deduct 1 mark. Okay, if you incomplete any one of these two statements, teacher might deduct 1 mark. Okay, and then for the derivation you get 2 marks. Okay, including this substitution. If you forgot to mention this substitution, teacher will deduct 1 mark. Okay, remember that. Next, describe an experiment to demonstrate the phenomenon of electromagnetic induction using a bar magnet and a coil. Okay, so this is the expression, this is the experiment of the demonstration where you have to draw this circuit first, draw it properly. I have seen students drawing very reluctantly. They are just, you have time, you can draw this diagram properly. Okay, so this is an easy question. If this question comes, this is an easy question. You can simply draw this diagram properly and then you can write the answer. When the magnet approaches the coil, the galvanometer needle deflects. Very easy to write. The diagram is easy. What you have to write is very easy. Only thing you have to understand, when the magnet is moving towards the coil, the galvanometer coil deflects. Okay. Now when you take it outside, or if you take it in the opposite direction, the galvanometer coil deflects in the opposite direction. Okay, that is the main purpose. Okay, when you taking it towards the coil, the galvanometer deflects in one direction. When you take it away from the coil, it deflects in the opposite direction. That opposite term is very, very important. When the magnet approaches the coil, the galvanometer needle deflects, indicating a current is induced. When the magnet is pulled away, the needle deflects in the opposite direction. This is very, very, very important line. Okay, showing that the current reverses. No current is induced when the magnet is stationary relative to the coil. This is also very, very important. Okay, now conclusion is important. You have to write the conclusion of this experiment as well. So diagram 1 marks, this writing 1 mark, conclusion 1 mark, 3 marks for this. Okay, this experiment demonstrate electromagnetic induction. A current is induced in the coil when the magnetic flux through the coil changes. This much is sufficient. I have written some extra information. Up to this much is compulsory. Okay, this demonstrate that when the flux changes in the coil, there is a induced EMF. Okay, you can write in your own words. Not necessarily you have to write whatever I have given it to you. If you have understood, you can write it using your own words. This confirms Faraday's law of induction, and the direction of the current follows the Lenz's law, opposing the change in the magnetic flux. This is optional. You can write it. It will create a good impression of you. Okay, if the teacher sees, okay, this student has understood the concept. So basically, in future, if there are some minor mistakes, as I always say, if you are writing some extra information that you know is correct, then in future some other questions where teacher might think, okay, should I deduct 1 mark? Maybe he will give you a benefit of doubt and give you the full marks. That's it. Okay, that's how you have to impress. You, the teacher who is checking your paper, does not know you in your final exam. Okay, obviously they are checking papers of the students they don't know. So that's how you make an impression. You talk to the teacher, sir, I am a good student, I know the answer. This is a way of talking to the teachers even without seeing their faces, right? Now question number 28. A horizontal straight wire 10 meter long is falling with a speed of 5 meter per second at right angles to a magnetic field 0.3 into 10 to the power of minus 4 Tesla. Find the instantaneous value of the EMF induced in the wire. Okay, so wire of the length of the wire is 10 meter, okay, falling with the speed of 10 to the 5 meter per second. Again, same formula, only thing is it is now a 3 mark question instead of a 2 mark question. So as you understand that this question can be a 2 mark question, this question can be a 3 mark question as well. Okay, maybe in some cases if it is 3 mark question, instead of giving it as a 5 meter per second, they might give you the speed in terms of kilometer per hour. So there will be one extra step involved. First you have to convert that kilometer per hour into meter per second. Okay, but the problem will be same. Be careful, all the units should be in meters. Okay, should be in SI units. So B is 0.3 times 10 to the power of minus 4, V is 5, L is 10. Okay, so it will be 50 times 0.3 is 1.5 times 10 to the power of minus 4 volt. Okay, so this is the induced EMF in the coil. So sorry, this is not 1.5, it will be 15. Okay, 50 times 0.3, right? So it will be 3 5s are 15. 15 times 10 to the power of minus 4 volt is the answer. Okay, next, Lenz's law is the consequence of the law of the conservation of energy. Explain. As I said, I will be answering this question while doing the objective questions. So this is a question where they might ask you, explain why Lenz's law is a consequence of conservation of energy. Let's see. When a charging magnetic field induces a current in a conductor, the current creates its own magnetic field. Okay, according to the Lenz's law, this new magnetic field opposes the change that caused it. So this is the introduction. This is the first part that you write about this, what is Lenz's law. You can directly write the statements of Lenz's law, that is also fine. This is how I have explained it. Okay, so when there is a change in magnetic field through a coil, the coil produces a induced EMF. Okay, produces a induced EMF in it, produced a current in it. Okay, according to Lenz's law, this current will produce such that it opposes the cause that creates it. Okay, so basically it opposes the creator. If the induced current did not oppose the change, it would create a runaway situation where, what is the runaway situation? Let's understand. Situation where the system gains energy without any input, violating the law of conservation of energy. So for example, let me explain it. Suppose there is a coil. You are taking a north pole towards the coil. Now according to Lenz's law, this coil will develop a north pole in its near end such that this repel it. Okay, this north pole will repel it. Now what would happen instead of north pole if a south pole was created? If a south pole was created, then if you push the magnet towards the coil, immediately there will be a south pole, and if you leave your magnet, then by default, by the law of attraction, this magnet will automatically get attracted towards the south pole. Okay, and because of that, the coil will continue to produce electricity even if you have stopped working towards the coil. So you just take the magnet, push it a little bit, and then automatically the current will continue to produce, which is not possible, which is not conservation of energy. So basically that violates the conservation of energy. So we are creating energy out of nothing, which is not possible, right? So that's why it is not, electricity is not free. You have to work to produce electricity. That's why electricity costs money. Okay, now for example, if you move a magnet towards the coil, the induced current generates a magnetic field that repels the magnet. You must do extra work to push the magnet closer, and this work is converted into electrical energy. Thus, no energy is lost or created. It is transformed from the mechanical energy to the electrical energy. So here we have explained what is the real process. In the real process, as I said, if you push a north pole of the magnet, it will produce a north pole here, right, and this north pole will repel the incoming magnet, and thus if you want to create more energy, then you have to push it further, you have to push it harder and with more force, right? So that way whatever work that you are doing, that work is getting converted into electrical energy. That is the principle of AC generator. Okay, in AC generator, this principle, the mechanical work done, is converted into electrical energy. That is the basic principle of any AC generator. Next question, a solenoid of inductance 2 Henry carries a current of 1 ampere. What is the magnetic energy stored in the solenoid? Simple formula, we know that magnetic energy stored in a solenoid is half Li square. Okay, half magnetic inductance is given by 2 Henry, I is 1. So basically it is 1 joule. The energy stored in the solenoid is 1 joule. Okay, so correct answer is 1 joule. So we have completed this chapter. I hope you enjoyed. This is a very interesting chapter, and I will be back with a new chapter, that is alternating current, on Friday. And if you like this video, don't forget to share it with your friends. I will be back. Till then, bye.